Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hi students. So we transitioned last time from looking at the nucleus, and we then looked at Compton scattering, and then we looked at this idea of isotopes, right? So let me give a brief rundown of what we discussed then. Then we'll take things a little bit further. So when we look at something like all these atoms, there is quantization of charge, and they have a fixed number of electrons, and so we have these properties which relate to their elemental nature, so the number of electrons and the behavior of those electrons, as this SPDF, various shells, and then their ability to then interact and form molecules. All that is dictated, largely from outside from the clouds of the around the nucleus, right? But the atom itself, right, is its charge is one quantized, because electrons exist in quanta of charge. There is no charge below 1.6 × 10⁻⁻19. You can't have a lower charge than that. And so they then came up with this second particle, which like the alpha particle, which is positively charged. But then there was a certain disconnect. So they found that there are a certain number of protons, but the mass seemed to be bigger than what they were calculating for electron. And fundamentally there is neutrality of the atom. And so the strong force that is, there is a balance of forces, right? And so the charge ratio, like for instance in this case, like QP by QE minus 1 is less than 10⁻⁻22, that is indicative of the full level of neutrality of the atom, right? So QP by QE, that is the charge of the protons, charge of the electrons, is almost 1. That's what they are saying. But then what they found was, like in something like vanadium, which has a total number of electrons 23, atomic number 23, Z equals 23, but the mass number is 50, right? So they then asked, so what is leading to that? And that's when, and then they found this whole idea of, for instance, carbon, which comes with, various isotopes. Then, hydrogen also comes with hydrogen, deuterium, and tritium. And then finally, polonium, which has a huge array of isotopes, which was, and then radioactivity that came from it, which was, of course, famously attributed to Madame Curie, right? Now, this led to the discovery of the neutron by James Chadwick. He bombarded light elements such as boron, and we already saw that, and alpha particles were obtained from the radioactive decay of polonium, right? And so, with these alpha particles. So when he found an alpha particle source like polonium, and these radioactive materials would naturally emit, alpha particles and beta particles, and then so they came from, from the nucleus of the particle, and so they would then go and, he put like a very low Z number, low atomic number element like boron or beryllium, and then he found that that some of these particles would just like kind of go all the way through, to go through wax, and then when they went and hit paraffin wax, eventually it will produce protons. You know, now there was the protons, and then there was another radiation, the neutral, when he put it when it went and hit the wax. Now the protons, um, they knew they were positively charged and they could measure that. But then there was this other thing, and which had like greater penetrating power than even X-rays. We started out with uh, uh, neutral radiation, and and this neutral radiation could further also eject electrons from a number of protons. So this was a very new particle, and so this was discovered by Chadwick, James Chadwick, and it was a later discovery. It is very surprising. So this gave rise to, so they said this bombardment of gives rise to two components. There's a third element there, and that is this neutron. They calculated using conservation of momentum, he calculated this particle to have a mass of 1.01 of the proton itself. So very, very similar and close to the proton, and so that led to our, what we found with from this, so so now we moved on, we are moving on, right? Now the question is, what is this other particle, and so I'm going to switch my slides now and discuss that. Okay, so this so typically, before I proceed, let me explain what you should be doing. You should actually watch the full video, particularly if you're interested in the material, and also in order to learn the material very well. So typically I recommend that you read say H.C. Verma and do problems at the end of it, and also take some time to really understand this. You must be watching the video, the IIT video itself. This is the process that I recommend for all physics students. Okay, so then you get our app and then solve problems. You checkbox all these three things, do due diligence. You will get wherever you need to go, particularly in material like this. You can learn it very well, and it will be there for you when you need to, for the long haul, when you need to apply this, in case you are so fortunate as to become a PhD in chemistry or physics, or like a engineer working in real high tech. There exists an equal. We all know there exists equal number of. We already discussed the neutrality of the atom, right? Now hydrogen has an atomic number of 1, while helium's atomic number is 2. But then helium's mass is 4 times that of hydrogen. They said there is something else, and therefore we use this notation: A for the mass number and Z for the atomic number. So when we say X, that is, and so let's say it was a C. C is carbon. Carbon is 6, typically 12, but then there were some cases when it was 14. And so then they had to explain this. Where did this come from? So they eventually found that there are 3 types of elements. There were, in some cases, there were isotopes. Isotopes have the same number of protons, but they have differing numbers of neutrons. Then there were these isobars. Isobars have the same A, and finally the isotones. Remember, okay, I'll help you understand this well. Isotopes has a P in it, so they have the same number of protons. All right, isobar has an A in it, same number of, same A. Okay, isotones has an N in it, so they have same number of neutrons, and neutrons is A minus Z. Okay, so Topes has a P, bars has an A, tones has an N. So whichever has the P has the same number of protons, whichever has the A has the same atomic number, same mass number, which is A, right? And whichever has the N has the same number of neutrons. Okay, so isotones, isotopes, isobars, so that is just to help you remember in case you don't do the due diligence. But it's better if you do the due diligence. So now the nucleus, as I've always explained, is very small, while the atoms exist in a cloud around the nucleus. Okay, so we are very soon going to be discussing nuclear force, and there are two types of nuclear force, etc. Okay, now what they did find is that when you look at the size, right, they found that different, like a smaller sized element had a different kind of shape, this curve shape, and so the nuclear size, right? Nuclear size, it varies just that little bit, and so now the two parameters A and Z, right? Z is, so why does it matter? Why do A and Z matter differently, right? It does, because see, the number of protons, right? If they were not held back together, they are in this tiny space and they're all sitting right there. They all have positive charge. They really want to get out of there. They're all pushing against each other and they are held in there, right? So there is that amazing force that holds this in such a tiny space. Okay, so now so there are these two factors, right? But mostly the size depends only on A. Okay, the mass is m times A, right? The volume is also related, and the radius is A to the power of 1 by 3. Okay, if V is equal to V naught A, right? The radius is obviously 4 by 3 pi r cubed, or roughly that, right? Cube, one third of that, right? So the volumes were roughly proportional. That's what they are saying here. The volumes are roughly proportional to the atomic mass. Not the Z. Not the atomic number, but the mass number. Which is A. Now, nucleus consists of neutrons and protons. 10 to the power of minus 15. You all know that 10 to the power of minus 10 is called an angstrom. Angstrom is roughly the size of one hydrogen atom. The nucleus itself is 10 to the power of minus 15. It is very small compared to the 10 to the power of minus 10, right? And so the mass is rho times the volume. Rho is the density. Rho is kind of constant, right? Because you say that the particles inside are pretty straightforward, and if you kind of assume that, then you have r cubed times, and r cubed is a function of A, right? So that's what gives you this rough A to the power of 1 by 3. Okay? So that is as far as the nuclear size goes. So what's now going on inside the atom? Okay, so so now we come to this idea of atomic mass, and then this idea of stability. So stability is a big deal, and I'm sure you understand why. In the normal scheme of things, as we live in this world, these things, they don't morph, at least in our lifetimes, right? Barring these radiational materials, which eventually does become lead, right? I already explained that, right? The rest of it it doesn't change. Like they don't let go of like a loose proton here, loose electron here. Go from this to that, right? There is a certain, some of these isotopes, they do radiate, lose a few neutrons. Eventually, they have a long half-life during which they decay from C14 to C12. We've already seen that. That's what is tapped to find out how old something is. When did the carbon go and settle there? And based on that, they kind of give it an age, and that's what we use in radiocarbon dating, right? So now there is a half-life for that, right? Anyway, so now the nuclear force and the nuclear binding energy, nuclear energy curve. Nuclear force is short-range force and acts for 10 to the power of minus 15 or less, right? Charge independent, they are not central forces. Magnitude depends on position, momentum, spin, and angular momentum. Forces between a neutron and a proton is attractive. That's the thing that you may not have guessed, right? In the electrical forces, like forces repel, like charges repel, right? But if there is something neutral, there is no attraction, right? So there's no electrical force. There's another force. This force is the nuclear force. Nuclear force between a neutron and a proton is actually attractive. The same magnitude, neutron, and proton. So they're all held in place, by that. It's all attractive. It's completely attractive. Okay? So now, and we already looked at this, van der Waal kind of potential energy curve, which kind of has a minimum, right? And and then so it hits a minimum and it sits there, and it takes a lot of effort to push it out of that minimum. It's always like that, inside the atom. So, and this 1 by 4 pi epsilon naught square by r is the potential energy. Potential energy is equal to 3 by 2 kT. Okay, so that is the nuclear binding energy, is the energy required to split a nucleus of an atom into protons and neutrons. Okay, it is always positive. The binding energy per nucleon is either a proton or neutron, is binding energy per neutron, the total binding energy divided by the mass number. So now nuclear binding energy curve, as the mass number goes up, right, binding energy per nucleon, it little bit decays. Okay, and so in very high, for instance, uranium kind of drops off a little bit. Okay, and so now as for A less than 20, the energy increases sharply. Okay, hydrogen, there is just a H, right? There's nothing that binds anything, right? Helium, there is just 2 plus 2, right? Now, but as you add more and more and more, it goes up and up, and then it declines rapidly. It gradually hits a peak at 56. 56 is our great iron. We live in the Iron Age, right? Now, the higher the binding energy, right, the more stable it will be. The elements with lower binding energy go through nuclear fusion and fission, right? Fusion, hydrogen, right? 4 hydrogen atoms, you fuse it together, it becomes helium, and then release of energy, right? Uranium, on the other hand, undergoes fission. It loses stuff, it breaks and becomes something else, right? So the mass of the nucleus is not equal to sum of the masses of its components, but lesser. Why is that? Okay, lesser due to its conversion onto nuclear binding energy. Okay, so that is what is called the mass defect. Okay, Z times MP plus A minus Z times Mn, that should give you the total mass, right? I have this many neutrons, this many protons, I sum it together, I should get total mass. But then when you put it in there, the total mass is lesser. That difference is this delta mx, and this delta mx times E is equal to mc square. You've all heard the equation, Mr. Einstein, Dr. Einstein, Professor Einstein, right? Professor Einstein. So the binding energy is that mass, is that delta mass times the square of the speed of light. Okay, so E is equal to mc square. That's what you get. Okay. Then, of course, see this equation, m naught by root of 1 minus v square by c square, this equation comes from special relativity. Okay. So E is equal to m of v c square. So mass velocity equation. P is momentum, m times v, right? And m itself is, of course, a function of the speed, right? Therefore, the energy is P square C square plus m naught square C to the power of 4. So there is this mass defect. It is, not so important unless you, of course, become a nuclear scientist and you're trying to save the planet from, or you're trying to, make nuclear energy for the benefit of mankind. And I hope some of you do get a chance, because you're all young, and some of you do become scientists, become engineers, and you go and work on what are going to be the large number of nuclear reactors which India is going to have, which use India's abundance. India is abundant in this element called thorium. It is greatly found in sands, what are called monazite sands, and so there you will, basically this is what happens with respect to nuclear energy. They convert that delta mx into energy and they release the remaining. Okay. So anyway, let's continue now. So yeah. So so EM interaction inside the nucleus. So Coulomb barrier, solar energy and fusion energy audit of this. Okay. Now as you know, sun is a very hot body and everything inside the sun is like plasma. Now so here there is a certain amount of electromagnetic interaction in the nucleus, right? Because a lot of protons sitting close to each other, right? And so as a result, so there is an interaction between those atoms, right? Those nuclear particles, right? And therefore, the V takes this kind of a equation, okay? And normally it should be this, right? Right? But inside the nucleus, the V, by that we mean the potential, right, takes this kind of an equation. Okay. Lambda times e to the power minus mu r by r. Normally you would expect this, right? Now, the Coulomb barrier is the energy barrier due to electrostatic repulsion particles need to overcome to go through nuclear fusion. So now hydrogen, 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 right? 4 hydrogen, right? Fuse it, release something, and it becomes helium. That's what goes on the sun. Okay. So, but then to really push these particles together, you have to get through what is called the Coulomb barrier. So you need a barrier energy of 30 million electron volts. Okay, so that is the Coulomb barrier. That is the thing you have to get over if you want to be doing nuclear fusion. Now, the solar energy, the temperature that is required to overcome the Coulomb barrier is very high. And so, at very high temperatures only, fusion can occur. Okay, such reactions are called thermonuclear reactions. So, where you push it all together and so in the sun, this proton-proton fusion cycle occurs through multiple pathways at lower temperatures due to high density particles. So can it happen without this kind of very high temperature? That has been one of the big questions. There have been people who have talked of fusion in a bottle at one time. Of course, that's never worked. Every now and then people feel they've done something when actually they haven't. And so the deuteron production weak process, right? How does that work? Basically, you take two hydrogen atoms, and you produce a deuterium, which is one neutron and one proton, right? And then you release a beta particle. E plus is a beta particle, right? So one of the positive charged nuclear particle, which is released, is called a beta particle, and so there is very, very slow, weak beta decay. So now, when you look at the Coulomb force, E square by R, right? The potential for 1 by 4 pi epsilon naught E square by R, then it is equal to K times T. T is, of the order of 10 to the power of 10. Okay. So, corresponding to that, R. Okay. So now, the other gain is when you have two deuterium particles, right? Then you have a deuterium and a hydrogen. Then they combine and then they let go of a gamma particle. Then they release a bunch of energy. This is how helium is formed. Okay? Notice that it's called helium, but it's missing they take two deuterium and they make a helium, right? And so it is missing a gamma. It is missing an extra number there. That is where the big energy comes from. So here they take a deuterium and a proton. Basically, one H1 is just a proton, right? Because the electrons are all gone. So now they take this and this. When they combine it together, it produces this and energy. So that is the fusion of these two. And so then there is this other burning route, which then takes these isotopes of helium, and then it combines to form another the more common element, helium, form of helium, and then two protons. And along with that, there's again a tremendous. See, finally, this is what we are all interested in, right? This is what we are interested in. These things, these three routes, right? We saw weak production process, produces very small amount of energy, 0.42. You have the neutron burning process, strong process, which produces almost 6 MeV, and this one is almost 13 MeV, where they form the real helium. So now this is a diagram which represents how solar energy is produced. H plus H, H plus H. Then you get this deuterium plus H, loss of energy and release of a gamma radiation. Then you get a helium, right? Helium isotope, Then you combine these two helium isotopes, and that then produces you this one and two protons. And then that cycle, so now you have these two protons. So now those two are going to go back and do this same process again. So there's a chain reaction. Okay. Therefore, there is tremendous, uh, energy released by this process, a self-engendering process. As you might have guessed, sun has been there for 4 billion years, right? So that's the idea there. So if you look at the energy audit of the sun is 10 to the power of 11 times the Earth. Okay, the radius of the core is 19%. Fusion power is 300 watts per meter cubed. Okay, and the protons are burnt, power is produced, and the percentage of power is 90%. So there is this. Then finally there is this carbon, and it goes from helium to carbon. So there's another cycle there. We looked at the hydrogen helium cycle. Now there's also a carbon cycle where these helium then eventually go towards, from helium they move towards carbon. Okay, so and that's another cycle, but we will not be going into that. So I think we are doing good time. So let me. So the last idea that we will look at in the context of the nuclear and nuclear force is nuclear fission. Fission is what happens in most nuclear reactors, right? As yet, they have not made a fusion reactor in the world that is commercially viable. So only most of the reactors are all fission reactors. There's fission and radioactive. So nuclear fission, there is the process of splitting of heavy nuclei into two or more lighter nuclei. Okay, so that typically the most common element is what is called uranium U-235. Okay? So otherwise there is also this U-238. These are all like isotopes of uranium, and so that is the most commonly used material. Then there is also plutonium, and then there are these reactors which use uranium, and then they produce plutonium as an output. And so those are called like fast breeders. Now process of splitting of heavier nuclei into two or more lighter nuclei. Right? That is the idea of nuclear fission. So now you break a atom into two constitutive elements, and then that releases a bunch of neutrons which go and bombard other atoms. And then therefore there is this what is called the chain reaction. Okay, so there is x1 plus x2, A produces x1 plus x2, then there is a something else that gets released, right? Then there are a bunch of beta particles. Okay, so now then there is also this gamma decay. So there is no radioactive decay analogous to atomic de-excitation. So no change in A or Z. And so gamma decay, neither A nor Z happens, but then it's like like something that's excited suddenly becoming less excited. So there is just continuous gamma decay from it. So, but gamma itself is energetic. So gamma radiation is an energy form of energy. Now the other one is this alpha decay. So we looked at first is the fission process itself. There is uranium, which then becomes lesser components, like now the second one we said is this gamma decay, where just gamma particles coming out from a excited nucleus, right? So the third one is the alpha decay, and we already looked at alpha decay when we looked at some of these experiments involving where they tried to find the neutron, right? For instance, Chadwick, he used some kind of material. So now let's take for instance plutonium 240, right? It releases an alpha particle, and that alpha particle is along with that you end up with uranium, and with the and along with that alpha particle. Alpha particle is essentially a helium nucleus. When they say H, they mean this. Okay, so so here they have so the mass number gets reduced by 4, the atomic number by 2, and then 4 and 2 is helium. So that goes out. Now, in that process, there is also the energy that is being released by the helium, and so now the difference in the sums, that is difference in the final sum minus the initial sum, is this. Okay, so this sum is greater than this sum plus this sum, because that is what produces nuclear energy. Mass gets converted to energy. E is equal to mc square. You take a mass and then you produce a energy from it. So that's what is happening in all these both fusion and fission reactions. So and in this case, mp minus md1 plus md2 times c square, right? The difference in that times c square is called the Q value. Q value is also defines the difference in the binding energy of the nucleus. Q value is the difference between the sum of the initial reactants and the sum of the masses of the product. Now, the next idea is when there is a decay of there can be either a beta decay or there can be a beta plus decay. Now, beta minus decay is a neutron, okay, which becomes positive by releasing a negative particle. Okay, so now normally if you have a beta plus, it is called a positron. Okay, so now this is not a beta plus, it's a beta minus. So here they are taking something and they are releasing a negative beta particle, and as a result you therefore have the Z going up. So one case is when carbon becomes nitrogen. Carbon is 6, Z is Z for carbon is 6, Z for nitrogen is 7. So you have C14, carbon 14 becoming nitrogen 14. Okay, so therefore this is this idea of beta decay. So to maintain conservation of charge and an electron and an anti-neutrino is produced. Now, beta plus is this idea of the positron, right? So a proton is transformed to a neutron. You all know that which is heavier? Neutron is heavier, right? We already saw that, right? It is 1.001 times the proton, right? A proton is transformed to your neutron. There is a decrease in atomic. Now, there is no change. The mass number itself will not change, but there is a small amount of mass that is lost. Maintain conservation of charge, positron and neutrino is produced. So it is that binding energy, nuclear energy, which is lost. So now we are now going to next discuss this thing called half-life. Okay, so now the rate of these decays. How many decays did we see? Nuclear fission, right, where something gets converted to different substances. That is the first one. Gamma radiation, right? Alpha decay, gamma decay, alpha decay, beta decay, right? So now, what is the law typically governing these decays? Like for instance, the radiocarbon dating. The law that governs this is that the number of these isotopic elements, the rate of change of the number is proportional to the number. dN by dt equals lambda times n. So now So how long does it take, right? So the rate at which it happens is dependent on how many elements. This is just like this Newton's law of cooling, right? d theta by dt equals lambda times theta minus theta naught, right? That is Newton's law of cooling, right? The rate of loss of heat is proportional to the temperature, right? Temperature difference with the surrounding. Like that, dn by dt equals lambda times n. Now, when you integrate, you typically the way they solve these differential equations is the variable separable method. Okay, so they move the lambda t to one side, dn by n. When you integrate dn by n, it becomes ln n. So ln n equals lambda t, negative lambda t. So you have e to the power of minus lambda t times n naught. Okay, so n naught times e to the power of minus lambda t equals n. That is the typical equation that you end up with. So remember how to do the integration. Remember that. So then the question is, what is called the half-life? So how long does it take for something to go from n to n by 2? That is a given number. Okay. So why is that a given number? Because because the equation, right? N equals n naught times e to the power minus lambda t, right? So now, if you had so for what t, right? Or you have, or you look at the log equation, right? So, the log equation, if you say, right? So, n naught by n log of n naught by n equals lambda times t, right? So that is basically it. So now log of n naught by n, so if you say n naught by n is 2, right? So that is half-life, right? Or half, right? So that is so you'll end up with some constant value, right? So then that constant value equals lambda times t. So that constant value, some 0.693 or whatever, some number like that, will equal lambda t. So now lambda equals something divided by, so lambda t equals a constant, right? So that is what we do. So I explained this before, right? dn by dt equals lambda times n of t. You variable separate them. dn by n equals lambda times dt. Integrate both sides. Ln n of t by n naught equals minus lambda t. N naught nt equals n naught to the power minus lambda t. So now half-life is the time for something to become half of itself. So if n of t equals n naught by 2, then what do you have, right? So then you have, on this side, you have n of t half, right? So this side will become half, and the other side will become e to the power of minus lambda t half. Take log of both sides, you end up with lambda t equals ln 2. Okay, lambda t equals ln 2 is some 0.693, something like that. If lambda t equals 0.693, yes, that is the thing. Now, mean life is a little bit different. The time at which all of the particles which decay, if the rate law throughout the decay remain the same as the rate law at t equals 0. What does that mean, right? So now this is a little bit different. Instead of this dn by dt, right, equals lambda n, right? You're now having a different equation altogether. N equals n naught minus lambda n naught times t. So it's a kind of linear kind of equation, right? It's a linear equation, right? Why is a linear function of x, right? X is time always. So this is the number of particles is a function of time, right? So now, so this is mean life. Okay, so and I think you can also derive that from this, but let me not belabor that point. Right? I suggest you take a moment to read this from your textbook. Okay, so now what happens when A goes to B and then B goes to C? Say you have unstable nuclei species, uh, uh, A1, which has a decay rate lambda 1, then it decays into A2, which has a decay rate lambda 2, right? So, and so on. So now when you have that, you then have the second equation being dictated by this, this kind of an equation. First one has the straightforward equation, right? But then this one, this N1 also has the second equation. So you then have a chain equation. So then now finally, if you put it all together, so when you have multiple processes, you have an A giving rise to multiple modes. So dn equals the sum of those lambdas times n of t. So dn by n equals negative sum of those lambda times dt. The ratios lambda I by lambda j will give you the relative decay rates for each of the daughter processes. Well, I don't know if they will ask you, multiple decay kind of chains, but I would, read up on it as well. Okay, so this is all the material that we have, and we cover it very, very quickly to facilitate your understanding. Okay, what you should do is you should spend some time reading this material either from HC Verma or from your NCRT textbook. You get our app, read it from there, and as you read, you also watch the corresponding videos and look at these slides. These slides that I showed you will all be available in those, um, along the way, even as you're studying from even as you're learning from the IIT PAL slides, you listen at least one time very carefully to the IIT PAL videos. Listen to all the IIT PAL videos, and then you can always come back and peruse these slides, because these slides can originate from the IIT PAL. So you will have both those, and then you have your textbook. Then you should do problems. Problems is very, very critical. We have added assessment now. You can go to external sites as well, and also our assessment is also very much going to be there, so where our own questions are also added in. So you have fantastic resources by taking our NEET, Sushruta for NEET or Ramanujan for JEE. Excellent apps at the most affordable price money can buy. The best apps you can get in the industry. We have now had enough right to claim that our apps are extremely beneficial to various students, and many of them are benefiting tremendously from using our apps and gaining from it. So with that, I'm going to close today's lecture, and I'll see you all again next week. Okay, so so if it's Saturday, it's for the class 11. If it's Sunday, it's for the class 12. We still have a significant amount of material to cover for class 12. there is semiconductor material, and then finally, the material with the truth table and all that, and then a little bit about X-rays. And so we'll get all that done, and that should give you more than enough material to get going. So now what I'm going to do after this is I'm going to kind of cover this material, as more new students join us, probably one more in one more round. But then this time I'm going to cover it in greater detail. This is to get you going, So for this year's students, since the last several months, we've covered the bulk of the material, so you can now do a lot of stuff with it. You've learned. It's to get you enough to going fast enough and further enough. So with that, I'm going to close today, and I'll see you all again next week. So on Saturdays, it's the class 11. Sundays is the class 12. class 11 people can, some of the material will come, but some of the other material you must start from the beginning and attend in sequence. Listen to, particularly electricity and reactance, listen to the whole material in sequence. Even this material, listen to it in sequence. But most importantly, use the app. App will get you going. App has everything that you need.